In this video, we are going to discuss tree diagrams and probability models. Tree diagrams are a tool that we've been using before to count the number of ways something could happen. We've also used tree diagrams to help create a list of all the different things that could happen. We are going to see now how we can adapt tree diagrams so that we can actually use them to calculate probabilities instead of just counts. Well, that's going to be part of our learning objectives. We need to understand how to build and notate a tree diagram. And then we want to check to make sure that we can use probabilities or calculate probabilities using a tree diagram and make sure our work is correct. So there's a lot of knowledge, understand, but the last thing is to build a probability model. A probability model is just a summary of saying, here are all the things that are possible. It's the way we'll take care of it is it'll be just a table. We'll see what they look like when we come up to it. So let's get started. I would like to note, you've probably seen that a lot of our problems, especially recently, can get pretty complex. There's a lot going on. And because there's a lot going on, if you are sloppy with your work or disorganized, it's going to create problems in figuring pieces out. We need a way to make sure that the work is organized and that your thoughts are organized. Tree diagrams are an excellent tool to provide that organization in a graphic, visual manner so that you can see. Let's see how a tree diagram could be used for calculating probability for this problem. At a restaurant, there are two breakfast platters that are served. One features pancakes and the other features eggs. There are also two choices for a drink. A person can order hot chocolate or juice. The restaurant owner tracks how often each platter sells, and she's learned that the pancake platter sells 60% of the time, and then the egg platter sells the other 40% of the time. Moreover, 70% of people choose juice and 30% choose hot chocolate. Assuming that our drink choice is independent of the platter choice, we want to build a probability model using a tree diagram. So all of that together should basically come and tell you this one quick piece. That whole paragraph basically boils down to this fact. Pancake was 60%, egg was 40%. Hot chocolate was 30, juice was 70. When we were doing tree diagrams before, we looked at it and said, okay, what are your choices? What's the first choice you have to make? You could choose pancakes, or you could choose eggs. From there, we said, got it, Garrett, we could choose hot chocolate or juice, hot chocolate or juice. Just listing the options, we could go through and create the list of all the different choices a person could make. That did not mean that every choice was equally likely. Because there are different probabilities, different percentages being put on these pieces, we can actually record that along the way. What's the probability that pancakes get picked? Well, this path for pancakes then is 0.6 for 60%. What is this path for the eggs? This path is our 0.4 for 40%. And we can actually record the probabilities on the paths of the tree diagram the whole way down. After you pick pancakes, hot chocolate is 30%, juice is 70. Hot chocolate is 30, juice is 70. Just writing down the probabilities along the way tells us not only what options are available, but we can also use it to create the total probability model. Where this gets to be very, very helpful is we can now start tracking down the pieces. Do you have your calculators handy so we can quickly crunch some numbers? If we want to get the probability of getting first pancakes and, whoa, that switched colors on me, and then hot chocolate, we can get just by multiplying the numbers on the paths. That's what independence did for us. So the probability of getting pancakes and hot chocolate, 0.6 for pancakes, 0.3 for hot chocolate. What is 0.6 times 0.3? You're right, Galen? That gives us 0.18. So this tells us 18% of the people who come in to buy breakfast at this restaurant wind up picking both pancakes and hot chocolate. We can track down another path, though, of pancakes and juice. Well, the probability of pancakes and juice, we can just multiply the probabilities written along the different paths. Pancakes was 60%. Juice was 70%. Just multiplying the two numbers on the paths tell us 0.6 times 0.7. That's 0.42, which is 42%. 42% of everybody who comes into the store to buy their breakfast gets pancakes mixed with juice. Well, of course, we have the third path now. Eggs and hot chocolate. Probability of eggs and hot chocolate. We just need to multiply the two paths. 0.4 times 0.3 is 0.12. And then our last one, and I'm going to need to scroll down for this one, and I'll use purple, eggs and juice. That's 0.4 for eggs, multiplied by 0.7 for juice, giving us 0.28. Well, we've got all these numbers. This is the basis behind our probability model. Using a tree diagram, we can list out the options, but putting the probabilities for each option on the paths allows us to multiply the paths in stages to get the overall probability. We can put those things summarized here. What was the probability of pancakes and hot chocolate? That was 0.18. What was the probability of pancakes and juice? That was 0.42. The probability of getting eggs with hot chocolate was 0.12. Then eggs and juice gave us 0.28. This is a probability model. Just this little table summarizing all the different things that can happen is a probability model. When we check the tree diagram, we can see there were four options. Pancakes mixed with hot chocolate, pancakes mixed with juice, eggs mixed with hot chocolate, eggs mixed with juice. So we're basically listing the sample space like we were doing back with our previous work. But besides listing the sample space, we're going to also write down the probability for each option. That's a probability model. The list of the sample space with their probabilities too. Now we can also do a very quick check to see if we're correct. This is the list of everything that they could pick, only four options. We know total probability has to be 1. And so we've got every single option listed out. In order for this to be a correct probability model, to know that we didn't make a mistake, we can take all of the numbers that we've got, add them up. When they add up, this number has to be a grand total of 1. Or with decimals, it's going to be 1.00. A total of 100%. If we get anything else besides 100%, we know that something has gone wrong. Maybe we multiplied incorrectly. Maybe we're missing an option. Maybe we wrote down a probability wrong, but something has gone wrong that has led us to not get the 100% that we know we need. So just adding them up. 8 plus 2, that's 10. 10 plus 2 is 12. 12 plus 8 is 20. So we'll carry over our 2. 2 plus 1 is 3. 3 plus 4 is 7. Plus 1 is 8. Plus 1 is 10. So we'll carry over. And we get exactly what we saw we needed to. Tying this back to our learning objectives. Do you know how to build a tree diagram? It's just creating the list in order like we were doing before. But are you also now putting the probabilities on the paths? That's the new part. With the probabilities on the paths, we can just multiply the paths to calculate the probabilities in order. If they add up to a total of 1, we know it's correct. This one problem is really the only thing that we need to be able to do for this entire unit, this whole little section. We should get some more practice, though. So here we go. The Eagles and the Warriors are going to play a best-of-3 basketball series. Oh, I spelled it wrong. Not are. That was supposed to be the word and. Thank you for correcting and seeing that I spelled that wrong, Kenny. I'll need to fix it on the file. The Eagles and Warriors are playing a best-of-3 basketball series. And we know how a basketball series goes. Whoever gets the first of 2 wins, they win the overall series, and they get the bragging rights. Suppose we have a 70% chance to win any game we play against the Warriors. Build a tree diagram and a probability model to determine the total probability of each team winning the series. Okay, so let's start off here. What's the first thing that could happen? Well, you play the first game. How could the first game turn out? The Eagles could win, or the Warriors could win. We're noting that if the Eagles win, they're up 1-0. And if the Warriors win, they have 1 win. You're noting I'm using the first number for the Eagles, the second number for the total number of wins for the Warriors. All right, so there's the first one. Now you got to go play game number 2. How could it turn out? Okay, so we could have the Eagles win or the Warriors win. The Eagles could win or the Warriors could win. With this setup, how is the series looking now? All right, on this branch all the way on the left, the Eagles won again, so that gives them 2 wins in the series. First to 2 wins it all, so this branch is now done. The series is over. We're not going to play anymore. But if the Warriors won, the Eagles had their first original win, and then the Warriors have a win. Neither team has 2 wins, so that's a branch that has to keep going. It's not over yet. For the Eagles, though, on this branch, oh, sorry, I didn't want to write that yet. This would have been the Eagles' first win. And if the Warriors won, that would have been their second win. That would have ended the series as well. Okay, so let's continue figuring out how else it could keep going. If the Warriors won, okay, so we have Eagles win or the Warriors win. The Eagles win or the Warriors win. So coming back down here, if the Eagles won, how many total wins did they have? That would have been 2 wins for 1 loss. The series is over. That would have been a win for the Warriors. The series is over. A win for the Eagles, it's over. Or a win for the Warriors, it's over. And now that we've got every single path that's over, we know that there's nothing else that could possibly have happened. This creates the tree diagram. This whole process right here is building a tree diagram to list out what could possibly happen. Now, you'll notice we don't have any of the probabilities written down. We built the tree diagram first, and now we can start filling in pieces with the probabilities. This is kind of the big one that we've got. The Eagles have a 70% chance to win any game. Well, if we've got 70% chance of winning every single game, that tells us every single path is a probability of 0.7. The probability that the Eagles win is 0.7. So what was the probability that the Warriors win? Yes, Sophie, that's 0.3. Continuing down further, probability that the Eagles win was 0.7. Probability for the Warriors, 0.3. Eagles winning is 0.70%. Warriors winning is 30%. 70%, 30%, 70%, 30%. And now we've filled in all the paths with the probabilities along the path, along the road. Please note, we're still looking back at our learning objectives. We know how to build the tree diagram. We know how to put the probabilities on the tree diagram. And now we're going to check to see how we can calculate the probabilities. All we need to do is multiply the paths. Okay, so what are all the different paths that could possibly happen? Well, listing them out, we could have Eagles win, Eagles win. That's one path. Noting that is Eagles win, Eagles win. What's the probability of getting that happening? Well, that was 0.7 multiplied by 0.7. What's 0.7 times 0.7? Okay, that's 0.49, which tells us, in this scenario, there's a 49% chance that the Eagles win the first 2 games. I'm noting that's an overall Eagles victory. All right, let's follow another path. We could say the Eagles win, followed by the Warriors win, followed by the Eagles win, tracing it all the way down to its end. Well, that's telling us Eagles win the first one, Warriors win the second, Eagles win the third. What's the probability for that all happening? 70% for the first game, 30% for the second, 70% for the third. What's the overall probability? 0.7 times 0.3 times 0.7. Thank you, Ian. That's 0.147, which still resulted in an Eagles victory. Okay, checking the next path then. We have Eagles, Warriors, Warriors. So coming down for that one, probability for Eagles then Warriors, then Warriors. 0.7, 0.3, 0.3, which would be 0.063 overall win for the Warriors. Tracking down the next path, I'm hoping that you guys are noticing having this tree diagram to provide the structure, listing out all the different paths you can take. That's one of the great benefits to the tree diagram because it gives you every single option. You're not going to accidentally miss one just because it's hard to see. We have Warriors first, followed by Eagles, followed by Eagles. So probability, Warriors, Eagles, Eagles. 0.3, 0.7, 0.7, which winds up being 0.147, an overall victory for the Eagles. And switching to green, we could then have Warriors, followed by Eagles, followed by Warriors. So extending Warriors, Eagles, Warriors, 0.3, 0.7, 0.3, which multiplies to give us 0.063, which leads to a victory for the Warriors. And we're lucky that we have only one path left, the last path. And I'll switch to, I don't know, this orange color. We have Warriors, followed by Warriors. So Warriors, Warriors, 0.3 times 0.3, which equals 0.09, victory for the Warriors. And so here is pretty much our probability model. It's a list of all of the different things that could happen. The list of different events are coming down the left-hand side, and their probabilities are over on the right-hand side. The tree diagram allows us to create this whole process. Now, we'll come back to actually answer the question. What was the piece that we were asked to do? And I don't know if people at home heard it, but Garrett was reading the last sentence. Build a tree diagram and probability model to determine the probability of each team winning the series. Does this ask us for the overall, like how they won, or just did they win? All it asks for is the overall probability that you won. The only thing that we really care about is the ultimate piece that says you could have the Eagles win the series, you could have the Warriors win the series, and we don't care if it was in 2 games or if it went to 3 games. The same way in the NBA, people don't care if you win the championship in a sweep or if they win it in 7 games. You get the ring either way. So we want to know what is the probability that this team wins the overall. What is the total combined probability that the Eagles win? Well, we can come back here and say, where did the Eagles win? The Eagles won for 0.49. The Eagles win for 0.147. And Eagles win for 0.147. Those 3 things combined lead to an Eagles victory, so we could come back and say 0.49, 0.147, 0.147. We can add up the probabilities for the 3 different ways the Eagles could win the series and get the total probability of them winning the series. Okay, so 7 plus 7 gives us 14. 1 plus 9 plus 4 plus 4 is 18. 1 plus 4 plus 1 plus 1 gives us 7. So we wind up with the total probability, 0.784, which we know is a 78.4% chance. So to build our probability model, we can just put in, it's a 78.4% chance that the Eagles win the whole thing. We still need the Warriors, though, to finish our probability model. So we'll come back and say, okay, what are all the different ways that the Warriors could win? 0.063, 0.063, 0.09. We've got to add up the probabilities for the different ways the Warriors could win. So 0.063, 0.063, 0.090. And when we add those up, 3 plus 3 is 6. 6, 12, 21. So we'll carry over a 2. So we get 0.216, which is 21.6%. Okay, so we'll come over and 21.6% chance for the Warriors. This is our probability model. Yes, it's a lot of work. Yes, the tree diagrams take a while. Fortunately, that's the big reason why you don't have like 10, 15, 20 problems for your homework. It's just a small number of them, because we know it's a lot of work. We should still check, though. We did all this work. Are we correct? One quick check is to say, add up the probabilities. If you add up the probabilities in your probability model, it has to be overall 100%. Do we get actually 100%? So 10, 10, 10. Yes, it's checking out, giving us further indication that we did it correctly. If we accidentally got something like 95, we'd want to go check our number crunching. Maybe we accidentally typed something into a calculator wrong. Maybe we made an error with our addition. Maybe we accidentally left something off. Maybe. But if you don't get the 100%, something went wrong, and you should start searching for what? All right, here's our last one. You are dealt 2 cards from a deck of 52. Basically, maybe you're playing blackjack or something. What is the probability that the 2 cards could be classified as a black card and a face card in either order? All right, so this is what we're looking at. We're dealt 2 cards. What are basically the options? We know that there are 52 different cards you could get, but we don't want to go through and put down 52 different paths. When we are looking at the path, ultimately, we want to know, did we get a success or did we get a failure? That's what we're trying to do. Make sure the paths are listing out success versus failure. For this particular one, we do not care if we get the black card first or if we get the face card first. We just need one of them to happen. Getting the success then for the first path, SUCESS, is getting a black card or a face card. Well, how many black cards are there in the deck? It's half, so there are 26 total black cards. How many more face cards are there that are red? Well, the face cards are Jack, Queen, King. So we could have Jack, Queen, King of ace, of hearts, diamonds, spades, clovers. Well, spades and clovers are already black, so we've already counted them. We have the 26 black cards plus the 3 face cards in diamonds plus the 3 face cards in hearts. the number of cards that gets us what we want is a total of 32 out of the 52. So this particular one would be 51, not 51, why in the world did I write 51? There are 32 out of 52 cards that give us success. So if there are 32 out of 52 ways to succeed, everything else is failure. If there are 32 ways to succeed, how many ways are there to fail? 30 subtract 30, 52 subtract 32. Garrett's correct. We've got 20 ways to fail. Okay? From there, we can now look and have another branch. When we go again, we could have the same issue that we want to have a path that leads us with success or failure. And this other path, we'd have success or failure. Oh, I wrote that in the wrong spot. Silly me. Success, failure. Okay, so now we are on this track that I'm outlining here with the star. What is the probability of getting the other card? Well, if we want black card or failure, black card or face card, after the first success, we no longer have 32 cards that are going to help us. One of them is gone. Since one of our successes is gone, that's going to leave behind 31 more. But since we've also removed that card, it's no longer an option to get, so we don't have 52 cards left. Now there are only 51. So we'd have 31 over 51 for the probability of getting success on the second card after we already got success on the first. And we could continue mapping out the other ones. The probability of getting failure on the second card. Well, there are 51 available. How many ways are there to fail? Well, there were 31 out of 51. If there are 31 successes out of 51, there are still 20 failures left. Moving to the other branch, both of these have 51 cards remaining. This whole second tier does, because in all of them we've dealt out only one card. But if we have removed one of the failures, how many successes are left? Well, we didn't remove any of the original 32, so that means we still have 32 successes to go with. But if we removed one of the failures, that means there are 19. And so this goes through and lists out the probabilities for each individual stage. Ultimately, this is what we needed to ask. What is the probability that the two cards are black and a face card in either order? This is asking us, what is the probability of getting success on the first card and a success on the second card? We don't care about the entire probability model for this particular problem because it doesn't say what is the probability model. The only thing we're asked to do is get, and I want to use a highlighter because I haven't used a highlighter much. No, that's crayon. Highlighter. And let's go with the yellow highlighter. This is the only path that we care about. And I should not have used a yellow highlighter because it covered up my probability. So purple highlighter. That's the only path we care about. So to get the probability, we just need to go through and multiply. Probability for the first one was 32 out of 52. Probability of getting success on the second one was 31 out of 51. We multiply that out, we'll have our answer. What's 32 times 31? Yes, that's 992. And for the denominator, 52 multiplied by 51, 2,652. And we get the probability that we were searching for. If we'd like to turn that into an approximate decimal, we can take 992 divided by 2652, and this is approximately, it's a decimal that doesn't stop, but that's about 0.3741, and I rounded it to the fourth decimal. The probability of winning, then, is about 37.41% of actually getting what you wanted it to happen. So, to sum up, whole point for what we were looking at today. Build a tree diagram to list out the options. We've practiced that one before. But put the probabilities on the paths, and then you can multiply the different paths to get the probability for each individual option. If you create and put that list of probabilities in a table format, you've built a probability model. And that's the whole point behind all of this. We want to calculate the probabilities, to build a probability model, put this table together by mapping out a tree diagram. If you've got that, you're all set for what you needed today.